Okay, so first of all, I'd like to thank the organizers for inviting me to give this talk. It's really a great pleasure being here. So I'm going to talk about the tidal disruption of stars by supermassive black holes, in brief, tidal disruption events, or TDEs. Now, TDEs are a relatively new field of research which has seen a rapid development in the recent years. TDEs were first predicted based on theoretical considerations already in the 1970s. And at that time, first ideas emerged where TDEs might play a role in astrophysical environments. For instance, it was suggested that the disruption of stars might be the power source of super galaxies and quasars. But then it turned out the rate is too low to sustain a continuous flow. It was also suggested that perhaps extreme tidal squeezing events might explain a peculiar variant of gamma ray bursts. Then in the 1980s and 1990s, one of the key questions in extragalactic astrophysics was, are there dead quasars in nearby galaxies? Or more generally, is there a dormant supermassive black hole at the core of every single quiescent galaxy? And it was Martin Weiss who suggested to use the distinctive manifestation of tidal disruption events in form of these luminous accretion flares as perhaps the most unique signpost of the presence of otherwise dormant black holes in the cores of quiescent galaxies, if they do exist there. Now, since the 90s, we have used other instruments, and especially the Hubble Space Telescope, to search for black holes in the most massive and most nearby galaxies. This is based on measuring kinematics of gas and stars at large distances from the black hole, but within its sphere of influence. This led to the measurement of 10 to the 7 to 10 to the 10 solar mass black holes in the number of nearby galaxies. However, this method does not work beyond the local universe, and it does not work for the least massive galaxies and least massive black holes. So a very complementary method is to use the destructive tidal forces on single stars in the immediate vicinity of black holes, and then the luminous accretion flares point us to the presence of black holes in galaxy cores out to very high redshift. In particular, they will be sensitive to a population of intermediate mass black holes. That is, black holes below 10 to the 5 solar masses, if these exist in large numbers in the universe. Now, furthermore, tidal disruption events are important laboratories for accretion physics under extreme conditions, down to the last stable orbit, and across a range of accretion regimes, very different accretion regimes, from potentially highly super Eddington to sub Eddington to basically zero on the timescale of months to years to a decade, unlike anywhere else among supermassive black holes. Active galaxies, quasars, take much longer to switch on or off. They are also a powerful new probe of the physics of jet formation in a regime very different from that of classical blazars. And a number of other interesting facets and application, and I'll mention a few of them during my talk. Now, a star is tidally disrupted once the tidal forces of the black hole exceed the self-gravity of the star. That happens at the tidal radius, and because the tidal radius and the Schwarzschild radius have different dependence on black hole mass, solar-type stars are no longer disrupted by the most massive black holes. They are rather swallowed whole because formally the tidal radius is inside the Schwarzschild radius. Where, for instance, the disruption of a white dwarf requires the presence of an intermediate mass black hole. After disruption, there is a high gas supply rate raining down on the black hole, producing a luminous flare of radiation peaking in the UV or soft X-rays. And simulations show that a large fraction of the disrupted star is actually on unbound orbit, and it orbits and escapes the system, while about some percent of the star is distributed a number of different Keplerian orbits around the black hole, returns to the black hole as a rate m dot proportional to t to the minus 5/3, and then if the matter is basically accreted as quickly as it falls back, then we expect the light curves to stay less t to the minus 5/3 in X-rays. Now the event rates are very low. You expect about one tidal disruption event per galaxy core every 10 to the 4 to 10 to the 5 years. So in order to search for and successfully detect these events, you need to sample a large number of galaxies. You need large or all-sky survey type of experiments. And such an experiment was carried out in the 1990s by the soft X-ray satellite ROSAT. Surveyed the whole sky in soft X-rays, then followed by a phase of pointed observations. And during these observations, the first few TDEs were detected. Let me very briefly summarize what was seen. So first, these events stood out as having very soft X-ray spectra in that survey and as being transient in nature. The X-ray luminosities, the X-ray peak luminosities were very high. The soft X-ray band, only in the soft X-ray band, so as luminous as quasars in soft X-rays. They did not remain at this high luminosity. They then faded away on the timescale of months to years. And the latest follow-up observations, deep X-ray follow-ups with Chandra and XMM a decade after high state, had shown that events basically vanished from the X-ray sky, implying amplitudes of variability exceeding a factor of 1,000 to 6,000. Now, what are the host galaxies of these events? Here's one example of the most nearby of these ROSAT events in NGC 5905, and the X-rays came from the core of this galaxy. Optical spectra were taken from these events, and the spectroscopy has shown that this is an H2 type galaxy, but all the other galaxies do not have any emission lines at all. So this is the spectra of totally quiescent, dormant galaxies. Yet they varied more in X-rays than any known quasar, much more. So black hole masses applying scaling relations are roughly on the order of 10 to the 6 to 10 to the 8 solar masses. You need about only a few % of the solar mass accreted to power the flare. And radio follow-ups were done in one case to see whether a radio jet was launched, and none was detected. Now all of these observations very well match the order of magnitude predictions from tidal disruption theory as given by Martin Rees in his early papers, were therefore interpreted as such. Now, more recently, the search for soft X-ray TDEs continued. There's a number of chance discoveries. There's also some dedicated searches now carried out with the XMM Newton Sleuth survey, for instance. Nowadays, whenever a new bright X-ray source is detected, we can actually much more rapidly tell it's special because we have the ROSAT archive database for comparison to now that an X-ray source was in high state. And while many events basically show the same properties than the first ones, revoluminous X-ray emission fading away quickly, there's also some very interesting exceptions, and I may talk about some of these later. Now next, let me talk about what I call spectroscopic TDEs. These are tidal disruption events which do come with emission lines and which have been mostly identified in the optical. Now, when a tidal disruption event happens in a gas-rich environment, then inevitably the luminous EUV soft X-ray radiation will photoionize any surrounding gas that will reprocess the radiation into emission lines, especially optical emission lines. And so we have here an unparalleled opportunity to reverberation map the gaseous core of a galaxy. And a number of events have been identified where this likely has happened. Let me briefly introduce to you the first such case, which was found based on the Sloan Digital Sky Survey database, which is an incredibly excellent database of the spectra of hundreds of thousands of galaxies everybody can work on. And this first spectrum here shows you the very raw SDSS image as you can retrieve it from the archive for every single galaxy. And you immediately notice, for instance, there is the automized SDSS pipeline classifies emission lines detected in every single spectrum. And you can recognize, for instance, Balmer line emission, hydrogen alpha, hydrogen beta, and oxygen 3. These emission lines are very common in astrophysical environments, in photoionized astrophysical environments. However, there's also a large number of strong emission lines which did not have any identification at all in the automized SDSS process. And it turns out that all of these are ion coronal lines from highly ionized ions. Also, there's very strong and broad helium-2 emission and strong and broad Balmer lines in that spectrum. Now, in order to form these ion coronal lines, in order to form the ions, you need to have a strong EUV or soft X-ray continuum because the ionization potentials are in the EUV or soft X-rays. So we checked the ROSA database, however, this galaxy was not even detected in X-rays at all. And so we triggered follow-up observations immediately after that. This happened a few years after the actual SDSS spectrum was taken because it takes a while until the spectra come into the archive and until we notice the source. And both the coronal lines and the broad helium-T emission faded strongly. The most highly ionized ion lines, you see again the initial SDSX spectrum and the first follow-up optical spectrum, they faded dramatically. There's broad helium-2, which vary. There's a very unusual broad Balmer emission with a redshifted asymmetric profile. These lines fade. We also took X-ray observations then. However, it turned out that the X-rays at low state, so a few years after this first SDSS spectrum, were rather faint. We triggered a Spitzer follow-up observation in order to search for infrared coronal lines. We did not detect any, however, we detected very luminous mid-infrared emission, implying reprocessing by cold dust. Now, in the optical spectrum of this galaxy, we can measure the stellar velocity dispersion and apply scaling relations to estimate the black hole mass, which is on the order of a few times 10 to the 6 solar masses. Now, all of these observations together imply that a very luminous EUV X-ray flare must have happened at the core of this galaxy. It was not observed directly. There's no simultaneous X-ray observations. However, we saw it in the lower energy continuum variability, and we saw it in a large number of broad and narrow emission lines, which then faded. Now, so what caused this luminous X-ray flare? The first question always when we see a new extreme transient from a galaxy is this an active galaxy? And the best way usually to tell is to look at the optical emission lines. This is a bit challenging in this case because all the emission lines vary. However, if you do use the low ionization emission line ratios, this indicates that we are not seeing an AGN. This is consistent with the absence of radio emission, the very faint low-state X-ray emission, the absence of an optical power law emission you see in AGN, and the iris, the infrared colors, and near-infrared colors imply an inactive host galaxy. So then, did we see a supernova? There is one type of supernova, the type 2Ns, which have temporarily spectra which formally look quite similar to these broad Balmer and helium lines we see. They also have some narrow emission lines. However, comparing with the whole database of supernovae, this event is very different by several orders of magnitude compared to all known supernova of type 2N. So for instance, if the X-rays come from the supernova, that would have been the most distant X-ray detected supernova ever. It would have been the most luminous mid-infrared emitting supernovae. Now, there's a small fraction of supernova which emit faint ion coronal lines, as in 1987A as an example. However, in this case, the ion lines were a factor of 10,000 more luminous. So there's a record holder among the few supernovae which produces these coronal lines, as in 205 IP. But again, the lines we see here are still a factor of 100 more luminous. However, the observations are well consistent with a total disruption event at the core of this galaxy, illuminating the surrounding interstellar medium, which produces the narrow lines, and perhaps illuminating the stellar material, which forms the temporary accretion list, this which forms the broad lines. Now, then after we found this first event, we carried out a dedicated search in the SDSS database for further such systems, the search criterion being first that they should have extremely strong ion corona lines, and second that in a first follow-up spectroscopy that lines would turn out not to be permanent but fade away. And then several more of these cases were found. All of them, in addition to the ion lines, show very broad helium-2 and very broad Balmer lines. Now, all events come from the very cores of these galaxies, and interestingly, all of these galaxies are dwarf galaxies with very low masses. If we use the stellar absorption features, they are not resolved by SDSS, so we can only put a limit on the black hole mass, which is less than about 10 to the 6 solar masses. Now, the overall similarity suggested that in all of these sources, the same mechanism is at work, and then estimating roughly the event rate, we end up about 10 to the minus 5 per year per galaxy in this order of magnitude fashion, consistent with what we expect for stellar tidal disruption events. Now, more recently, several more of these events have been identified in transient searches, in transient factories in general, and in dedicated supernova searches in particular. This identification then, of course, is in the optical. These events have very well covered optical light curves, so you can nicely follow the actual optical luminosity evolution. And all of them, here's a selection of some of these spectra, all of them, like the first events, come with very strong broad helium-2 emission lines. Most of them also come with broad Balmer lines, except with a few exceptions where the hydrogen emission is almost not detected. Now, so these broad hydrogen lines have then been interpreted as rising from the stellar tidal debris, which formed the temporary accretion disk. A puzzle then has been, why is our Balmer lines lacking in some of these sources? So an early suggestion was that maybe we have seen the disruption of a helium-rich stellar core. This is still under discussion because also photoionization and optical depth effect might lead to the absence of Balmer lines. And so our next speaker, Ira Akavi, will talk much more about these interesting optical systems. Now, the first high-resolution X-ray spectroscopy of a tidal disruption event was only carried out recently. Again, this was thanks to an optically identified tidal disruption event in the Assassin supernova search. And rapid follow-ups show that this event comes with luminous X-ray emission. And therefore, the XMM Newton X-ray spectrometer was used for the first time to obtain a high-resolution X-ray spectrum of this system. And this has revealed the presence of a number of narrow, deep absorption lines of highly ionized gas. Now, we can measure the outflow velocities in the gas. It turns out to be a few hundred kilometers. These lines are variable, suggesting they arise in the black hole environment. And then Miller et al. Interpreted their observations that in the sense that we are seeing the early formation and evolution of an outflowing disk wind, or perhaps the stellar material itself. So a very powerful new diagnostic, but you need nearby luminous events and you need to do quick follow-ups. Okay, a new chapter in the study of tidal disruption events was opened when Swift detected a very unusual event, which turned out to be the first jetted TDE. Now, Brett in his talk on Monday already briefly introduced this remarkable event. It was discovered in 2011 by the Berthollet telescope. There was no detection ever of this event 3 days earlier before this first data point. And then it showed quite a remarkable light curve, high amplitude variability, very rapid variability down to timescales of 100 seconds. The very first guess was that this is a gamma ray burst, however then the X-rays faded much more slowly than from known gamma ray burst. The second idea was maybe a galactic transient, however then quite soon the host galaxy was identified. an optically inactive but star-forming galaxy at this redshift, which then also implies a very luminous, if isotropic, X-ray emission of a few times 10 to the 48 ergs per second. And there's a variable near-infrared transient also from the very core of this galaxy, so again establishing this as the host galaxy. Further unresolved variable radio emission was detected from the core of the host galaxy, and all of these observations together were then interpreted as the launch of a powerful jet following the tidal disruption of a star at the host galaxy of the system. Now, SWIFT kept monitoring the system on an almost daily basis. Here you see the long-term X-ray light curve, which shows an overall decline. But superposed on this light curve are fluctuations, and suddenly, about 1.5 years after the initial high state, the X-rays dramatically faded away, no longer detected by SWIFT, only in deep follow-up observations. At the same time, the radio did not show this deep drop. It developed in a smooth way that immediately implied that there's different emission sites of these X-rays, and the radio at that time will suggest that perhaps in X-rays we are seeing a transition from a super to a sub-Eddington accretion disk. Now then, the late time X-rays, which you see here, could only be measured in a number of pointed deeper observations by XMM Newton and Chandra. Interestingly, these remain constant, and the X-rays are quite hard, and there have been several suggestions what powers this low state non-variable X-ray emission. One was by one of our previous speakers today that we are actually see X-ray scattering from surrounding gas. Another idea was that we see the forward shock from an outer jet, or perhaps that there's a permanent low luminosity AGN. However, the X-rays are still, even in low state, they are still more luminous than you expect from given the host galaxy, the very low mass host galaxy of this event. Or perhaps that we see viscously spreading of the accretion disk and then the accretion disk corona, which makes a relatively hard X-ray spectrum. Now, this event being so well covered and so luminous triggered a large number of theoretical follow-up studies, looking, for instance, at the mass and the possible spin of the black hole, or discussing the physics of jet formation, for instance, the role of magnetic fields in AGN and magnetohydrodynamic jet formation models. We think that we need a large-scale magnetic field, while the disruption of a main sequence star would not have produced such a field initially. Also, looking at the very outstandingly luminous X-ray emission. Is it due to beaming? Could it be due from an accretion disk, but which then would have been dramatically super Eddington? Is it due to shocks from jet ISM interactions? So there's two recent observations which shed new light on some of these issues. One is the highest radio observation ever of this system. This is based on the European EVN, European VLBI network, and the goal was to measure the spatial extent of the source or to follow the motion of the radio jet. Now, in order to do so, you need a nearby steady point-like reference source, and then a resolution of about 12 micro arc seconds could be achieved, or 1/20th of a parsec in the host galaxy of J1644. Now, no motion was detected of the jet ejecta, then implying an apparent jet velocity of less than 0.3 c. So this may imply that the jet has slowed down from an initial superluminal phase. However, it's also interesting to note that this maximum jet speed of 0.3 c is predicted by recent simulations of jet formation under in a purely radiative way under supercritical accretion. Now, another recent piece of evidence on the nature of the disk jet systems comes again from X-rays and from the detection of an X-ray reverberation signal. Now, this is an XMM Newton spectrum of this system, and there is a presence of a fluorescent ion line. Now, this ion line shows two interesting features. First, the ion line is blue shifted, implying that it's reflected off high velocity gas on the order of 0.1 C or larger. Secondly, the red wing of this ion line, presumably formed by gravitational redshift, is variable and varies in response to continuum changes, and this implies that it must arise in the close vicinity of the black hole. These observations together were then taken to interpret the ion line as arising from the funnels of a super Eddington accretion disk, highly in outflow. Okay, so most of the tidal disruption events observed so far are broadly consistent with the disruption of a solar type star. However, in the case of SWIFT-J 1644, it has been pointed out that several features of the remarkable light curve can actually well be explained if it was a white dwarf which was tidally disrupted. That's an idea of C. Piran and Julian Krolik. Now, white dwarfs, disruption of white dwarfs is of particular interest also in the context of the emission of gravitational waves. Now, if you have a solar type star which is disrupted, then the gravitational wave signal is weak, and only if it happened at our own galactic center could the first generation of space-based gravitational wave interferometers detect such an event. However, if the star is a stellar end state, a compact stellar end state, a white dwarf, a neutron star, or a stellar mass black hole, you would produce detectable gravitational waves. And white dwarfs are of special interest because the partial disruption of a white dwarf would also produce an electromagnetic signal. And so we could use this electromagnetic signal to pinpoint the gravitational wave source. Now, there is one extragalactic globular cluster which has been interpreted in terms of a white dwarf tidal disruption by the intermediate mass black hole, and this is work by Irwin et al. I'd like to briefly mention it. So there is a globular cluster. One of the globular clusters in the elliptical galaxy NGC 3099, which is part of the Fornax cluster of galaxies. Now, this globular cluster has two interesting and very unusual features which are not observed as such in most other globular clusters. First, there is a luminous X-ray source at its core, which was persistent for a while but then started to fade away. Second, its optical spectrum is very unusual. So this is just part of the optical spectrum. There is relatively broad, forbidden emission lines in the optical spectrum of this globular cluster. You detect strong oxygen-3 emission, strong nitrogen-2 emission, but there is no Balmer emission at all, which in most astrophysical environments you expect a strong Balmer line. And so Irwin et al. Suggested that the luminous X-rays imply an intermediate mass black hole, and that the absence of Balmer emission implies that it actually was a white dwarf which was tidally disrupted. Now, so far I talked about tidal disruption in single black holes. However, recent work has shown that TDEs are also very good signposts for the presence of supermassive binary black holes. Now, supermassive binary black holes form in the course of galaxy mergers, and then upon coalescence, they are the loudest source of gravitational waves in the universe in the frequency regime of the upcoming space-based gravitational wave interferometers. Therefore, an intense search for this supermassive binary black holes is currently ongoing electromagnetically, and a challenge identifying the systems is that you need at least one of the black holes, or both, to be active in order to identify the binary system. However, many galaxies might harbor supermassive binaries at their cores, and if none of them is accreting, then nowadays we have no chance at all in detecting them, with one exception, and this is through tidal disruption events, because the tidal disruption rates and the tidal disruption light curves will look characteristically different if they occur in a supermassive binary black hole system. And there is one candidate event, one TDE event, which may have happened in a supermassive binary black hole. This is based on a light curve analysis, and let me briefly summarize these observations to you. So first of all, this event J1201 was discovered in our dedicated search for tidal disruption events in the XMM Newton database. At first glance, it seemed to be quite a normal TDE, very high peak luminosity, overall decline in the first year, light curve, no emission lines detected at all, so a quiescent galaxy, no radio detection down to deep limits, so no powerful jet launch, with a black hole mass on the order of 10 to the 6 to 10 to the 7 solar masses. However, if you look closely at the light curve, there's some puzzling features. It shows a very sharp dip by about a factor of 50 or larger within a few days. Then it remains faint for quite a while. Then it recovers to close to its previous brightness, and it's dipping a second time. Now, in principle, a number of scenarios suggest themselves to explain the system. Like if you had a precessing jet and beaming effects that could produce the observations, however no radius and no jet is detected. If you had extreme absorption in these low states, that might produce a dip, however in the high states no excess absorption at all is detected. Also, we do not detect an emission line reprocessing signal in our repeat optical spectroscopy. However, this light curve looks very much as what has been predicted a number of years ago by Liu et al., who simulated tidal disruption events under the presence in binary black hole conditions, where the second black hole acts as a massive perturber, temporarily interrupts the stellar stream onto the primary black hole, and then causes characteristic dips and recoveries in the X-ray light curve. And just running their models on this particular case, they found that there's more parameter space where these models agree very well with the observations, and this then requires a milliparsec supermassive binary black hole with a mass on this order and mass ratio 0.1. Now, if the binary black hole interpretation is correct of the system, then there's a number of implications. So at about milliparsec separation, this would then be the most compact known supermassive binary candidate, which has long ago overcome the so-called final parsec problem. So the black holes kept merging through this critical phase of 1 parsec. They will continue to shrink to the emission of gravitational waves and then be a prime source of gravitational waves in the E-LISA band. And currently, this is the only method to detect supermassive binary black holes at the cores of quiescent galaxies, with the single exception of our own galactic center, where we can, with the single exception of our own galactic center, where we could look at spatial motions. So in order to assess how many of these systems are out there, what we really need is well-covered X-ray light curves to follow these dips and recoveries. And a proposed future mission, which would have these excellently covered X-ray light curves, is the Chinese mission Einstein probe, a new soft X-ray or sky survey type of mission, which has the TDEs as one of their main goals, the observations. And Xuanan Chang later in his talk will briefly introduce this mission. Okay, so most of the events I've so far talked about are relatively short-lived events. Yes, both those identified in X-rays as well as most of those identified in optical or UV, they are noticed close to their peak luminosity and then they start fading. However, there is at least one event which showed an extremely long, bright X-ray phase. Now, it was first noticed as a TDE candidate in the XMM Newton database. It showed a relatively rapid rise, while on the timescale of months, to relatively bright X-ray luminosity. Then follow-up observations somewhat later showed that the luminosity has increased further. Also, the event shows a remarkably soft X-ray spectrum, so very few photons detected beyond 1 keV. Now then, when we kept following the source further with a number of swift observations and deeper XMM and Chandra pointings, it turned out that the X-rays remained rather bright. So they fade away, but only by a factor of 2 to 3, and on a timescale of 10 years, the X-rays remained rather bright. So this is very different from the first soft X-ray TDEs discovered with Rosat, where we have a similar timeline for follow-up observations, and they faded by a factor of more than 1,000 within the same time interval. Then interesting is also the host galaxy of this event. This is a very low mass galaxy, a dwarf starburst galaxy with no detectable signs of any ongoing AGN activity, with a black hole mass on the order of 10 to the 6 or perhaps lower. So overall, this observation suggests that we have seen a very long-lasting TDE with possibly, now if you take the X-ray luminosity in combination with very low black hole mass of this galaxy, then it implies that at least we see the source accreting at the Eddington luminosity. Possibly these extreme super soft X-ray spectra, as they have been phenomenologically observed in super accreting stellar mass black holes, may point to the fact that we even see a super Eddington accretion phase. Now, this is of interest, seeing this long-lasting Eddington or super Eddington accretion in such a low-mass black hole is potentially of interest for understanding the black hole growth in the early universe, because given the highest redshift quasars and the masses they have, the black hole masses they have of 10 to the 10 solar masses, you can show that sub-Eddington or even Eddington accretion may not be enough to grow these black holes in the time they've had to grow at the large distances, so the early cosmic times they have been observed. Now, in order to power the light curve, you need more than a solar mass star to be disrupted. The data are roughly consistent with a massive star, either a 10 solar mass star, which is relatively rapidly accreted but has a lot of mass, or a 2 solar mass star, which accretes in a very low viscosity regime. Okay, so in summary, we have observed by now about around 40 tidal disruption events identified in X-rays, UV, optical, then followed up, some of them detected in the radio. Now, in the future, when we detect these events in the thousands, in the hundreds of thousands with upcoming sky surveys, for instance, in the optical with the Zwicky Transient Factory or with LST, in X-rays with a mission like the Einstein probe, in radio with SKA, then for the first time we'll be able to do statistics. We'll be able, for instance, to assess the frequency of intermediate mass black holes, or to look at the tidal disruption rates in the dependence of host galaxies, dwarf galaxies with its massive ellipticals, mergers with the single galaxies. Now, the events we have seen so far already told us that TDEs exist. They have pinpointed us to the presence of supermassive black holes and otherwise totally normal, inactive, quiescent, inconspicuous galaxies. They have opened up the first window in studying accretion physics under extreme conditions and studying the physics of jet formation in a regime this is very different from the classical Blazar regime. Different black hole masses, different accretion rates, different large-scale magnetic fields. So all of this is very interesting. However, what we'd like to have is even more rapid follow-up observations to identify these events in the rise phase, very sensitive follow-up observations at high cadence and at multiple wavebands, and then this will allow a wealth of new applications using these events. In particular, there's this new discovery space of using TDEs as signposts of supermassive binary black holes and searching for supermassive binary black holes via well-covered X-ray light curves. And I didn't talk about the recoiling black holes, but these would appear as off-nuclear TDEs or as no-host TDEs. And then, of course, in the longer distant future, we look forward to the first detection of gravitational waves from void dwarf intermediate mass black hole systems, along with the electromagnetic counterparts. Okay, thanks for your attention.
So yeah, we have time for questions.
So for that one convincing intermediate mass black hole event, is it possible to just have a rough idea of the event rate for such things in the universe?
Mm-hmm. It's a good question. I mean, there is theoretical work looks a lot of this because this extreme mass ratio inspire was of extreme interest for the space-based interferometers. Now, from this one observed event, I think we cannot estimate a rate because that was not a systematic search for such event. It was a chance discovery because I just studied this particular globular cluster.
Where are the theoretical questions? I mean, did you have any predictions of these events? Did you compare to models? Where is deficits which you want to help modeling with the observations? You had this one chat. I just saw the picture. I didn't go into the details. So,
okay. There's many issues. Well, there's two aspects. Early models predicted, for instance, the event rates, looking at the predicted event rates. So basically, we have compared them in this order of magnitude way. There's many uncertainties in theory. There's many uncertainties in using the sky surveys to estimate a rate. They agree well. There is a number of key questions, like how the stellar material evolves, how much of the matter is ultimately ejected, how much is accreted, how much drives a strong wind, what is the efficiency of the accretion in any epoch of the evolution. Now, there have been a lot of simulations of these events. Potentially they're extremely challenging. Relativistic hydrodynamics in full 3D, non-steady flow, and really great progress has been made in recent years looking at different phases of the tidal disruption event, either the early squeezing or the actual disruption event. The interesting aspects are, for instance, to try to use light curves to measure black hole spin, because the tidal disruption event light curves will look different if the black hole is rapidly spinning. You know, just the way you go down to the less stable orbit is closer and you accrete in a different way. The exact rise to maximum and the decline is different. That would be highly interesting to apply these models, for instance, as a new route of accessing black hole spin. What you do need is very well covered light curves. We have nicely covered light curves in the optical, but that emission may come either from an atmosphere of the accretion disk or from shocks in stream-stream collisions as the stellar debris returns to the black hole. In X-rays, we see the actual accretion disk emission as it evolves, but there we cannot have daily light curves at this stage. You might with future mission, and that is one of the reasons for this great excitement for future soft X-ray missions like the Einstein probe, because that will give us very well-covered X-ray light curves.
Mm-hmm. Whether I'm the permitted to use more time. I mean, I have expected more to be pointed now to potential possibilities to learn about the black hole properties, spin of the black hole, maybe also the possibility of probing the near horizon region. Is there any attempt to use the data for that?
I think we need better covered data. A key would be extremely well-covered light curve at multiple bands. But like with all transients, it's extremely challenging to do rapid multi-wavelength follow-ups, to go deep and do the monitoring. For instance, the Swift event, just the question of jet formation is a very interesting one. And the Swift event sort of, in a sense, we did expect the soft X-ray TDEs. The emission line reprocessing is immediately obvious, at least of the surrounding gas. We did not necessarily expect that these powerful relativistic jets are launched by the style disruption events. And it's in a very different regime from the jets we see in classical blazars. The accretion weights are higher, the black hole masses are lower, there is no large-scale magnetic field, and it's a very pristine environment without any previous activity. So likely we are learning a lot of that, but we are just in the process of interpreting all this data and improving the modeling under this difficult, this non-steady situations.
Okay. I may missed your interpretations. Is there any, what is the reason why the decade-long sustained long event, why it does not decay like a characteristic T to the minus 5/3, it's decays so slowly?
Yeah, so the reason is that we may see a more massive star, that we disrupt a very massive star and then the gas supply is higher, and so it declines, but in a more slowly fashion. Another possibility is that the viscosity of the disk is lower. Most of the event, and that was one of the initial arguments of Martin Rees, that the style disruption events, we expect extremely high viscosity of the disk, relativistic precession, stream-stream collisions, and the matter goes in quickly. If for some reason in this event you have a lower viscosity regime, then the accretion would be more slowly.